So the last thing that we need to be able to do in this chapter is when you have a reduction happening at the cathode, how much of the metal, especially if it's a metal that's reducing, how many grams of it are going to add on to the electrode? This is a process that we're all familiar with. It's called plating. You've heard of gold-plated jewelry, I assume. Gold-plated jewelry is a not very expensive metal that's just covered with gold. Well, the way that they plate gold on jewelry is with electrolysis. Literally, the jeweler has an electrolysis setup, and they have gold in solution. They run electrons into it. The electrode in that case is the necklace or the bracelet or whatever, and they will reduce gold on there. So the metal, the electrode in there, gets heavier because it's having a metal ion gain the electrons and become the solid metal, and it adds on to the electrode. So what I have here is a zinc and iron reaction, but there is a power source pushing the electrons from the iron to the zinc. So these zinc ions, as the electrons come in, the zinc ions migrate over here, they grab onto those electrons, they become solid zinc, and the bar of zinc gets heavier. So that's the process of plating. It happens in jewelry, it happens a lot of times in automotive and industrial parts. Rather than painting things with a sprayer or a brush, they'll actually coat them by, the people in the industry call it dipping. They'll dip the parts in an electrolysis setup, and that will coat them with, with the metal that is coming out of solution and adding onto it. So we need to be able to calculate what mass of the metal is plating onto the electrode. What mass of it. Now there is a stoichiometry setup for that. It does look intimidating with many steps to it. For most of these problems, there's going to be 5 steps. But it's just a stoichiometry setup, and it really is not too bad. You're not going to find this to be confusing or daunting at all, because the units will pretty much tell you what you need to do next. One thing that we do need to have our brain wrapped around is when we do electrolysis, we do need to be able to know what the current is. We've been talking a lot about voltage, but not current. Current really tells us how many electrons are flowing through the wire, where voltage is based on how hard the electrons are being pushed based on how reactive the anode and cathode are. The current is how many electrons are going through. So current is measured in a unit called amps. Amps are named after an Italian guy named Ampere. Amps are coulombs per second. So it's like measuring how much charge per second is going into the cathode. So that if you know how much current you have flowing, remember current is coulombs per second, and you know how much time has gone by for this current to run, you can figure out how much charge has come in, and then we have Faraday's constant that relates charge to how many moles of electrons you have. If you remember, Faraday's constant is, Faraday's constant is 96,485 coulombs per 1 mole of electrons. So we have a relationship between coulombs that have come into the cathode, where the reduction takes place, and how many moles of electrons that is. And if you know how many moles of electrons, and you know what the oxidation number is of your metal, I'll go through this in examples. It's pretty simple. Whoops. Oh my gosh. I don't know how I did that. Okay, we're right here. Okay, so all these are conversion factors. And let's just go through. I think it'll become very clear when we do an example. So this is the typical kind of example that we'll see. What mass of these substances can be produced in 1 hour? So we turn on electrolysis setup and we just let it sit for 1 hour with a current of 15 amps going through. So our power supply is cranking out 15 amps. It's going constantly for an hour. So if we have in our cathode cobalt ions and we want to plate cobalt onto the electrode, we're going to get metallic cobalt from this ion. How many grams of the cobalt are going to plate after an hour? That's what the question is. So here's what we do. And again, I'm just following this procedure. The first thing that we have to do is get our time value or unit into seconds, because we need to be able to convert the seconds away from the unit amps. So the problem here says we electrolyzed for 1 hour. Well, we'll start with that, 1 hour. Now we have to get it in seconds. And I assume that all of us can figure out how many seconds are in an hour. If you're in physics or you've taken physics, you do this all the time. But if you're not sure of that, you have to go to minutes and then to seconds. I trust that you can go right from hours to seconds. For every 1 hour, how many seconds? Physics man, Mr. Daniel, how many seconds in an hour? You seem like you're ashamed of that. You're ashamed of being physics man? Yeah, I don't blame you. Chemistry is so much better. I would mumble my physics answers too. So that's good. I'm proud of you. Okay, so now we've canceled our hours out. So now we're dealing with seconds, and we have a relationship that involves seconds. It is this thing right here. The current that was running was 15 amps. That means 15 coulombs every second were coming into the cathode. So that's a relationship that now is going to take us to 15 coulombs every 1 second. Now those seconds cancel those seconds, and we have the charge. So 15 amps gave us that conversion factor. Now the next thing, we have coulombs. What do we know about coulombs? Oh, we know Faraday's constant. Faraday's constant says that there is 96,485 coulombs, and that's related to moles of electrons. Every 1 mole of electrons has a charge of 96,485 coulombs. So this calculation has told us how many moles of electrons have come into the cathode. Now we're getting close, because if we want to know how many grams of cobalt have plated, we know how many moles of electrons we can relate. Look at this relationship up here. We're going from cobalt plus 2. You see how cobalt has to gain 2 electrons to become neutral? So if I have a mole of cobalt ions, it needs 2 moles of electrons to all become neutral. So that's our next conversion factor. We need 2 moles of electrons for every 1 mole of cobalt that reduces. And that takes us out of moles of electrons. Now we have moles of cobalt, and the last thing is how many grams? 1 mole of cobalt, and the molar mass, 58.9. I can't remember. 58.9. Okay, so even though there was a lot of conversion factors, it's not that bad. I mean, like I say, the units kind of tell you what you do next. And so we just crank this thing out, and when you crunch the numbers here, 3,600 times 15 divided by Faraday divided by 2 times 58.9, you get to 2 sig figs, because the current was in 2 sig figs, 16 grams of cobalt. So electrolyzing for an hour, we get 16 grams of cobalt plating on our electrode. With 3.5 minutes left, I'm going to ask you to try one more. I know that we're tight on time. Will you take a look at this problem? We have an unknown metal. We're going to call it M. It undergoes electrolysis. The M is going to reduce. It starts as this solution. M nitrate is going to be dissolved in water. You can see what the formula is. You need that. You know how much time the electrolysis took. You see what the current was. It tells you how many grams of the metal were plated. So the question is not how many grams. It tells you that. The question is, what metal is M? Can you identify M? So there's a little bit of a twist to this one, but take a couple minutes and see if you can figure it out. Come on, you're running out of time.
I don't know if you can see the numbers on the periodic table. I'll see if I can get this to stay down now. Ah, there it goes.
Okay, our time is almost up. So yeah, you can see that they didn't ask you to go through the exact same process, but we did use the same essence. We start with time, use the current to get coulombs, use the Faraday constant to get moles of electrons. We see that M is a positive 3 ion, so it takes 3 moles of electrons to reduce every mole of M. So we get number of moles. There's another way to do this algebraically too, so if you didn't follow this, it's totally fine. But molar mass is grams over moles, so we have the grams, we have the moles, divide, and we get around 209. I'm going for bismuth. You might have gotten polonium too. They've got very close molar mass. May there be non-breaking porous cups and electrodes and high voltages in your future. See y'all tomorrow. Thank you, fourth hour.